Merci beaucoup. Merci à tous pour être venus et merci pour cette invitation. Je suis vraiment très honorée de parler ici. Et excusez-moi si je ne peux pas parler en français, je vais parler en anglais, mais si vous avez des questions en français, ça va aussi. Okay, so the title of my talk today is How to Prove Things with Diagrams. And this is also the title of a forthcoming book for Oxford University Press I've been writing for a while. And so here today I want to give you the gist of the book and some of the main ideas in there. So here is the plan for my talk. So first of all, I'm going to give you an introduction and a sort of like contextualization of this work within a recent trend in philosophy called the philosophy of mathematical practice, and then give you a little bit of an introduction of the philosophical debate about the epistemology of diagrams. And then I'm going to dig into two different case studies of diagrams. One are diagrams for surfaces, so arrow diagrams to represent topological surfaces, and the other ones are commutative diagrams used in homological algebra. And here I chose two different case studies also to showcase the heterogeneity of diagrams in mathematics. So a lot of studies have been focused solely on geometric diagrams, and I think this is a mistake. This has impoverished the discussion. And in this context, I'm going to be quite brief with respect to the mathematical details, which are not super sophisticated, and rather spend more time to discuss the philosophical relevance of these cases. And in particular, I'm going to discuss diagrams as forming notational systems. So we're going to see what notational systems in mathematics are and why they are important. And then I'm going to argue for a somewhat controversial thesis that our diagrams not only can be used within proofs, but sometimes they are even essential to the proofs in which they figure, and we'll see what this means. So let me then introduce the topic. So the philosophy of mathematical practice, I just thought I'd say a few words since this is the first lecture of the series in the philosophy of mathematical practice. So it refers to a broad cluster of approaches in the philosophy of mathematics that take seriously the activity of doing mathematics. So I also started my academic career as a mathematician, and it was natural for me to address philosophical issues that arise from mathematical practice. And one could say that the philosophy of mathematical practice kind of is a reaction, in some sense, to the narrow focus of traditional philosophy of mathematics in the 20th century, which has basically focused on two main topics. One is the foundation of mathematics, and the other one is very general questions about abstract objects and our access to them. But as completely neglected some of the philosophical issues that arise when we look at mathematics as its practice. So then the philosophy of mathematical practice wants to endorse a bottom-up approach in which often people present case studies and try to read philosophical things from them, both contemporary and historical case studies. Moreover, one of the characterizing traits is a rejection of a highly idealized historical conception of mathematics, and so try to bring the level of idealization down. Another thing to note is the openness to interdisciplinary research, and obviously, philosophers of mathematical practice are going to talk to mathematicians, and this is a perfect example of this. But not only, they're also going to talk with historians of mathematics, or people working on mathematical cognition, or even sociology of mathematics. And the questions tend to be localized. Maybe some questions don't arise for all branches of mathematics, but are really pertain to certain domains, as also the question that will interest me today. And here, another slide on the philosophy of mathematical practice. This is a book that came out in 2008. It's edited by Paolo Mancosu. And I think this part of the introduction is really good to give a sense of the spirit of this movement. So he writes, the authors in this collection believe that the epistemology of mathematics needs to be extended well beyond its present confines to address epistemological issues that have to do with fruitfulness, evidence, visualization, diagrammatic reasoning, understanding, explanation, and other aspects of mathematical epistemology which are orthogonal to the problem of access to abstract objects. So kind of broaden the set of questions. So let's then dig into diagrammatic reasoning. So often one thinks that diagrams are useful to discovery, and nobody objects that. So the fact that diagrams are a useful heuristic tool is uncontroversial. The problem often is whether we can actually use diagrams to prove. And this is the focus of my talk today. A lot of work has been done to analyze Euclidean diagrams. And in fact, many scholars, like Menders and then Avigard and Mumma, have shown that the use of diagrams in Euclidean geometry is highly regimented. They even created formal systems, formal diagrammatic systems for it. And so they show that diagrammatic reasoning is reliable and leads to stable results in Euclidean geometry. So diagrams can perhaps be used in proof. But then, we also know that diagrams in the history of mathematics have really led people astray in the past, especially the type of diagrams that enable a sort of visual intuition that was proven to be utterly unreliable with the rigorization of analysis. For instance, all the familiar example of continuous nowhere differentiable curves and all things like that. So there was, Hans Hahn called it a crisis and intuition that in some sense led also to abandon diagrams in modern mathematics. So the suggestion would be, okay, perhaps diagrams can be allowed in Euclidean geometry, fine, but not in more modern branches of mathematics. And that seems like the received view. So in modern mathematics, however, they could still be important as tools for speeding up communication, for instance. Here in a very influential paper by Thurston on proofs and progress in mathematics is right. Mathematicians use wide channels of communication that go far beyond formal mathematical language. They use gesture, they draw pictures and diagrams. So, okay, like something like helpful to speed up communication, but not really at the core of what we really care about, proofs. So is this correct? So it seems like this view is also endorsed by influential philosophers of mathematics. And here I love this passage because it really expresses vividly what I want to argue against. And this is by John Burgess from a book called Rigor and Structure from 2015. He says, some diagrams are surely no more essential to the proofs in which they appear than the illustration that accompany many Victorian novels on first publication were essential to the literary value of those works. And here you have a nice illustration from the Mill on the Floss by George Eliot. Other diagrams may play a more important role, especially perhaps this type of abstract algebra, where what is called diagram chasing is ubiquitous. Though even here, the kinds of diagrams that are chased seem only to abbreviate information that could be put more cumbersomely and in a way less easy to take in words. So here you see there is a strong skepticism with respect to using diagrams in proofs. So the thought would be reconstructed something as follows. Diagrams, perhaps, like other devices mathematicians use in their reasoning, can be disregarded as epistemologically irrelevant alternative ways of presenting information that can be conveyed in words. So Burgess say, oh, either they are like illustration and just like totally superfluous, or even if they're not superfluous, okay, we can just translate them in words, so who cares? Let's just forget about them. But then no, I think this is mistaken precisely because propositional content is not all that matters from the point of view of individual justification and knowledge. So if we are interested in pursuing an epistemology of mathematics that is faithful to mathematical practice, then this move is not going to work at all. And second, I think behind this skepticism lies the mistaken thought that there is no principled way of distinguishing reliable from unreliable use of diagrams. This is what happened with the crisis on intuition. Basically, the idea was like, oh, some diagrams can lead us astray, then maybe let's ban all diagrams. But in fact, I think we can provide some tools to actually distinguish between those diagrams that can be used rigorously from instead illustrations that are maybe not so regimented. So I'm going to argue that there is. So here are my main theses. One, some diagrams form mathematical notational system and therefore can play a non-redundant role in proofs. And two, there is a plausible conception of proof, a plausible for the context of investigation we are in, according to which diagrams are not just abbreviation for more cumbersome non-diagrammatic displays, but can be essential to proofs. And this doesn't mean, obviously, that we couldn't prove the same result in a way that didn't involve diagrams at all? Of course we can. But what we would do doing so, we would not create a different presentation of the same proof, but rather a different proof altogether. So that's the main thought. And to argue for this, I'm going to look at two case studies, as I mentioned before, of arrow diagrams and commutative diagrams. So let's start with arrow diagrams. So here is a diagram that probably you're all familiar with. I think it's a great example for how we reason with diagrams. So we have an illustration of the Möbius band, and then arrow diagrams of the Möbius band, in which obviously, like the diagram has some conventions we have to know to interpret it correctly. And these conventions are, okay, we have a square, and we have two arrows. The arrows are actually to be interpreted as gluing instructions. And the gluing has to be done in such a way as the arrow match. So in this case, the arrows are in two different directions. So we have to imagine stretching the square. So we are working with topological objects. So we don't care about metric properties. And then we twist and glue. So this is a gluing instruction. So now it's a quick question for you. So what happens if I cut the Möbius band along its core? So along the red dotted line. Maybe you know this because you know it already and you remember, you tell me the answer, fine, but that's not very interesting. So I'm interested in how do you get around to finding the answer to such a question. So you can look at this and try to imagine in your head what would happen. Very hard. If you are like me or like most of us, that's not going to be a good way to do it. It's going to be quite complicated. But I'm going to show you, in fact, I mean, it's a simple example, but I think it's pretty telling that we can use arrow diagrams as a notational system, reason with them, and find the answer. And here it is. So we just take our diagram. I drawed it as a rectangle, but it's the same. And we go ahead and actually cut it. So we have now two little pieces. And then we have to take care of, OK, what was glued to what. So I can't, whatever. So, but we have the double arrow convention that works in the same way. And then we glue, and then we glue again. And guess what? Wow, it's a cylinder. Striking. Something I do, just like reasoning with the diagrams. Actually, when I ask this to my students, they normally, and I say, how do you get the answer? They normally just like, if they have like a scissor, etc., they just do it physically. But this is like a better way to do it. So you can reason with the diagrams. And cutting and pasting, it's not only an intuitive terminology to guide us in imaging diagrammatic transformation, it's also an intuitive terminology, but it also corresponds to precise mathematical operations. So gluing corresponds to forming a quotient space, and cutting is the inverse operation of gluing. So then when my students listen to my class and then I prove them, oh, it's a cylinder, then they come to me with this like object and they're like, are you sure? In fact, it looks kind of weird when we do it physically. And in fact, this reveals another interesting thing about these diagrams. They are not diagrams of embeddings. They are diagrams of abstract surfaces. And in fact, like the diagram of the Möbius band, as I told you, was to be interpreted as gluing instructions where I have to twist to make the glue connect. But I never said you have to twist just one half twist. You could do any odd number of half twisted you want, and you still get the correct surface. So in this case, actually, you would get a cylinder that's not canonically embedded in space. OK, so this notation is very useful because it can be generalized. And so from a square, of course, we can go ahead and keep gluing the sides that were not glued before to obtain surfaces without boundaries. So here I start with a cylinder, and if I glue in the same direction the other two sides, I obtain a torus. And in fact, like a very interesting thing is that this piece of notation is not just to solve little problems, but can actually be used to prove the classification theorem for surfaces, which says that any closed connected surface results from gluing the sides of a polygon according to two gluing instructions for the orientable ones and the non-orientable ones below. So this is just to give you a sense that this notation can also be used in advanced mathematics and to prove significant results. And in particular, here is a step of the proof by Massey from 1991. And here is just to give you a sense that these type of diagrammatic proofs can be also found in graduate textbooks in mathematics and not just in my talk. And so here, basically, you have a cutting and paste technique in this little piece of the proof. And from the first diagram, we are like, oh, how can we go from 1 to 2? Basically, we cut along C. So the first diagram has this internal arrow that just represents a cutting instruction. So basically, we cut along C and then glue along B. And so the second diagram, the B is a sort of like scar from the gluing. Then the third diagram is the same as the second, but where we erase the scar and add another cutting instruction and so on. So we can perform really this cutting and pasting in order to prove significant results. So this was the first rather quick, but I think already telling example of how we can think with diagrams to prove things. Let me say something about the diagrammatical notational system. As you already saw, these diagrams were not just evocative illustration, but we are using it following specific rules. Arrow diagrams, in fact, do not pose the risk of overgeneralizations that is typical to geometric diagrams. They can be used reliably. I mean, geometric diagrams can also be used reliably, but there are a lot of discussions with respect to the problem of overgeneralization. How can I reason with a particular triangle and be sure that I'm not using some specific property of the drawing? And it's very famous Klein fallacious proof that all triangles are isosceles for that. But these type of diagrams do not present that at all because they are topological diagrams. And the fact that they can be used in proofs can be explained by two facts. So one, they satisfy some well-formed desk condition, and in fact, we can give a precise syntax for these diagrams, and they are subject to precise rule of manipulation, so that tap onto our intuition of 2- and 3-dimensional space, but correspond to precise mathematical notions. So they form a notational system. But what does this mean exactly? So mathematical notational systems are representational systems of various kinds that we use in mathematics. They are systems formed by external objects deliberately invented as tools for communication and reasoning, and they are endowed with intended interpretation and use. So I'm going to focus here on written or otherwise drawn in 2-dimensional surface notational system. Obviously, you can think of extending this with 3D notational system, but by far the most common ones are the written ones. So here is a detour on another case study. So my first case study on working on diagrams with knot diagrams, so I can never leave them out on my discussions. So, but just very briefly, a knot is there are some equivalent definition, but for these contexts, we can define them as a smooth, closed, simple curve in 3-dimensional space. So the mathematical knots are just abstraction of regular knots. So for instance, we have a knot with strings. The difference is mathematical knots are always closed, and they are 1-dimensional, so they are curves in space. So intrinsically, they are all homeomorphic to S1. What really matters in this case is the embedding, how they are living in space. And in general, we are not interested in the geometric shape of a knot, but rather in the way it's knotted. So we work with knots up to equivalence. So two knots are equivalent if there is an ambient isotopy transforming one into the other. And roughly, this means we can transform them one into the other without cutting them and repasting or making one strand go over the other. So when we work with, in knot theory, we work with knot diagrams. These are controlled representations which display only a certain number of properties of knots. And we start from a knot in space, and basically to obtain a diagram, we project the knot on a plane or any other surface, actually, sometimes in the sphere, and we keep the information at crossing. So as you see here, a first example of knot diagrams, I have the information at the singular points of which strand is over and which is below by using this convention, which is like the interruption of a line. And this convention is particularly useful from a cognitive perspective because it makes it very easy for us to imagine this two-dimensional thing in space as a three-dimensional curve. In order to be a diagram, the projectile has to be regular, so some constraints have to be met, like we have only transversal intersections and only two strands intersect at a time. Okay, and so this is a complicated knot diagrams, and later I'm gonna show you what knot is equivalent to. So operative dimensions, so one of the key features of notational system in mathematics, both diagrammatic and not, is that we can calculate with them, we can do things. So elements of a notational system can be combined or mentally manipulated. In the case of arrow diagrams, we had the cutting and pasting techniques. Also, we can do other things like connected sums. With knot diagrams, we have a theorem called the Rader-Meister theorem that basically connects the mathematics of knots to the mathematics of knot diagrams and tell us that any two knot diagrams can be, that represent the same knot can be transformed one into the other with a finite sequence of these three finite diagrammatic moves. But what is interesting for us now is that when we reason with knot diagrams, we can easily, with our imagination, spatial imagination, see equivalences between different knot diagrams. And here in particular, you see that I simplified these complicated knot diagrams a little bit. Why? Well, like this strand we see that it's on top of everything, so I can just like take it and put it down like I did here. And here I have just a more simple representation of the same knot. Okay, so it looks like notational system, the way we represent mathematical objects matter to the way we reason in mathematics. And this is something like other scholars have observed. For instance, Sullivan says it might be tempting to suggest that a mathematical object by any other name would be just as useful, but we have seen that this is not so. Sometimes the names encode properties of the object in question, and in such cases, other names would be less revealing. In short, properties of the notation are important to mathematics. And in fact, Sullivan says, it seems like very compelling. Properties of the notation are important to mathematics. But then a further question is, which properties exactly? So not all properties are going to be mathematically important. Some properties are perhaps only cognitively important, like the size or color of the test. So, but if I write the same algebraic equation in a font or in another font, it seems like it's not a mathematically important aspect of the notation. It's just a cognitive difference, perhaps. And so that's why I introduced this distinction between enabling and constitutive features of a notational system precisely to pinpoint what are the important aspects that make a difference in mathematics. So each notational system presents clearly identifiable and reproducible constitutive perceptual features like lines, interrupted lines, arrow, dotted lines, etc., which can carry mathematical content. Other perceptual features are just enabling, and this applies across the board, so to both diagrammatic and non-diagrammatic notations. And in particular here, I give you an example. So these two diagrams are in fact the same diagram. Why? Because color is not a constitutive feature of knot diagrams. Color is just an enabling feature. I need it to be of a color just to see it. And you know what? It can make a huge difference. If I gave you the same diagram in light yellow, you're like squinting, maybe not being sure what knot was represented, but it would not be a mathematical constitutive property. This doesn't mean that color are always irrelevant. In fact, there is like the simplest knot invariant that is used to distinguish knots that's called tricolorability. And in order to compute it, we have to color, not diagrams. Fine, but in so doing, we are obtaining a different notational system with a different set of constitutive properties. So I think like this distinction, enabling constitutive property, is key to understand how notational systems are also individuated and which changes make a difference. So here, it's another example. I just wanted to put it from Byrne, 1847, is a colorful edition of the first 6 books of Euclid. And just to give you a sense of, in practice, color obviously can matter. Sometimes they carry mathematical information, like in the colorful edition of Euclid. Okay, so my suggestion then is that diagrams form mathematical notational system, and that in general, all elements of notational system must satisfy certain constraints. And this is also the basis of why diagrams can be used rigorously in mathematics. And the constraints are the following. So clarity, the constitutive perceptual features are clearly identifiable and stable. Reproducibility, the constitutive perceptual features are reproducible. And usability, the operations defined on the notational system are cognitively manageable. So these constraints are almost trivially satisfied in general for non-diagrammatic notational systems, but they are not for diagrams. And that's why I think led to some sort of like the skepticism I mentioned before about the use of diagrams in proofs. So just let me go through them quickly in turn. So the first constraint is clarity. So the constitutive perceptual features, so those features that carry mathematical content must be clearly identifiable. This means that the informational content of an expression in a notational system can in principle be reliably carried by a finite number of propositions. Obviously, like our perceptual system is finite, we don't have like infinite resolution, etc. And here is to give you an example, okay, like this can be interpreted as a knot diagram, but this can't, and it's precisely because it doesn't convey clearly the constitutive feature, which are like the number of crossing, etc. I would not be able to do anything with that thing, although they are just like pictures of the same three-dimensional objects from different perspectives. One can be interpreted as a diagram, the other cannot. Nevertheless, these can be interpreted correctly as an illustration of the same object. Reproducibility, so the constitutive perceptual features are reproducible, so it must be possible for an average practitioner with appropriate tools to copy an expression in a given notational system. So we have to be able to reliably reproduce things. And that's why also it has been emphasized by Manders and others for Euclidean geometry, like the features that can carry mathematical content are the ones that are stable under small perturbation, because we are not going to copy precisely the diagrams. And third, usability. The constitutive uses are cognitively manageable. So the manipulation of the notational system must also admit a description in terms of proposition. And this does not mean, key thought, that the manipulation on a notational system and its conversion are necessarily on a par from a cognitive and epistemological perspective. So although all the passages, all the type of manipulation I perform on a diagrammatic notational system do have a counterpart in a non-diagrammatic notational system, this doesn't mean that the two things are equal. And here is the example from before on the knot diagrams and how I can manipulate it using visual imagination. And in fact, the first, going from A to B, you already saw the simplification, and then you can perform similar moves, and then, oh, guess what? It was the unknot all along. Okay, so a couple of words on codification. So I already mentioned that these constraints is what makes it possible to code diagrams, in fact. So arrow diagrams obviously present a straightforward algebraic interpretation. We can label the edges of an arrow diagrams with a code, an algebraic word, and then have something like A1, B1, A1 minus 1, B1 minus 1, etc. This can be useful, and it is useful, in fact, but transforming the diagrams into such algebraic words would obscure their topological meaning. So the fact that arrow diagrams can easily be coded might give the wrong impression that, after all, diagrams are mere abbreviation or other forms of display. That was John Burgess thought at the beginning, which, by the way, I'm proud to say he changed his mind. So, just about knot diagrams can also be coded, and that's very easy. So knot diagrams, like all other diagrams, are discrete representations. They have a finite number of crossings. I can just like associate numbers in specific ways to this crossing, and I get a numeric code. So nobody denies that. Okay, so now before discussing a little bit more the relationship between these diagrams and their codification, let me present briefly the second case study, which has to do with a totally different type of diagrams, algebraic diagrams, and as you will see in a second, in this case, the codifications are even more straightforward, precisely because they are algebraic from the starting point. So I think it's important to look at algebraic diagrams, especially because traditionally they have been neglected. So traditionally, the focus has been on geometric diagrams. At some point, when I was first working with algebraic diagrams, I got some criticism by the community in the form of, oh, but those are not really diagrams. I'm like, come on, but they're called diagrams. Everybody called them diagrams. So algebraic diagrams not only like are diagrams, but are by far the most common diagrams used in contemporary mathematics. So these are algebraic notational systems extending into dimension, and these would open up the discussion for a different talk about what are diagrams in fact. But I think it's very plausible to say that even if they are not geometric or topological, they are still diagrams because they are called diagrams, etc. Okay, so here is the quick example I want to show you, and it's an example of commutative diagram used in homological algebra, so where we can perform the so-called diagram chasing technique. And I think, obviously, like commutative diagram are used a lot in category theory as well, and there are like a lot of other things to be said. But I think like this proving technique is particularly helpful here because I want to focus on specific way of calculating or reasoning with diagrams. And here we have abelian groups in a commutative diagrams such that the rows are exact, and we have certain extra properties. In this case, F2 and F4 are surjective, and F5 is injective. And then we have to prove that F3 is surjective. And then there is like a symmetric claim, but I'm just going to focus on this first one. And basically, the idea is to exploit the commutative diagram to prove this property, the surjectivity of F3. What does this mean? It means, okay, I can take an element, and basically I want to find a pre-image under F3. So that's like what I want to prove. Obviously, this is what I want to prove, so I can't just assume it. So the idea is like, okay, I take a little B3 and move it around the diagram, chase it around the diagram until I find the desired pre-image. So first of all, I can just like take its image under beta 3. Okay, I have B4. And then guess what? I can go up because F4 by hypothesis was surjective. But then I know that the rows are exact. And so I have that the composition of two maps is always 0. But then F5 was injective, so I have 0 also there. And then again, the rows above are also exact, so I can go back. And here becomes a little bit more tricky because I can't go down directly from A3 to B3, but I can suppose that F3 of A3 is B3 prime, and then I substitute from B3, B3 minus B3 prime to have something that gets sent to 0. So I'm not going to go, these details are besides the point and now a bit quick. But the idea is like, so instead of B3 now, I take B3 minus B3 prime, so it has a 0 image, and so I can take the image, pre-image in B2. So I get a B2. And then by hypothesis, I had the surjectivity of F2, so I can go up and have A2. And then I finally can use the commutativity of the diagram and find the pre-image of B3. So that's was very quick, but kind of just to give you an idea of how we reason with this type of algebraic diagrams and why their two-dimensional configuration actually does matter to prove things and also to discover things. So this is one example, but in fact there are many examples, and in fact books in the topic are going to say after a while, oh, you just prove by diagram chasing. So it's like a thing that you do often. And another example is like the fundamental theorem of homological algebra also involves, in this case, an infinite diagram, but it involves the same type of technique, chasing elements around a diagram. Here I just showed different paths. Okay, so what can we say about this case study? So commutative diagrams do not present the problem raised by topological diagrams, so they are akin to algebraic notations after all. There is no appeal whatsoever to spatiotemporal intuition like there was for geometric or topological diagrams. And it's easier also compared to the previous one to see how diagrams could be eliminated. I could just write in lines all the relations. So, but if I do that, I can do it even easily, but our understanding would be compromised. The fact that they're easy coded does not mean that they are dispensable. And as the name suggests, they are still diagrams, and a diagram chasing technique supposedly needs a diagram. So visual thinking, that is visually perceiving a diagram or imagining moves, is essential to follow proofs by diagram chasing. One can follow a diagram-free counterpart stepwise, but one may still be in the dark of how individual steps contribute to larger scale section of the argument and how the sections fit together. It's much easier to keep track of what's going on when we follow the diagram chasing in the diagram. And the relative cognitive efficiency applies not only to following an argument, but also to discovering an argument. Of course, when we look at the diagram in its entirety, we can easily imagine what possible moves are next to prove the desired property. So commutative diagrams, in a sense, are like maps, are like underground maps. So experts have to interpret statements they want to prove in terms of different paths in this abstract map. A diagram chase consists of moving elements around a map in an algebraic world, one could say. And as for maps, there is an interaction between the text and the diagram. It's not that the diagram works alone, so we are guided by the text in what to do, where to go, but we do it with the diagram. So here, then I presented the two case studies, so let me discuss some philosophical consequences and try to argue for this more controversial claim of the essentiality of diagrams. So here I take from a blog post from 2007 from Professor Gowers, who was actually inquiring about properties like explanatory proofs and other properties of proofs, but then realized that even understanding when two proofs are the same is not easy. In fact, he writes, even the seemingly more basic questions, when are to prove the same, was pretty hard to answer satisfactorily. And in fact, there are many examples that seem trivial but are not. So Euclid's proof that there are infinitely many primes, for instance, often people say it's a proof by contradiction. In fact, it's not, but it's very similar to a proof by contradiction. It's kind of the same idea behind them. And some people would say, oh yeah, it's the same proof. And in fact, in his blog, Professor Gowers also has a similar example and saying, obviously, it's like the same proof because it's so easy to go from one to the other. We know exactly what to do. But then, if you ask to an historian of mathematics, he's going to say, not at all, very different. Or if you ask to a logician who is interested to define logical structure of proof, they're going to say very different. So it seems like maybe the way we identify proof is not fixed once and for all. There is not one correct answer. It's going to depend on what is the context of our investigation. What do we want to do with our concept of proof? It's going to make a concept compared to another more useful or appropriate for that context. Other changes, anyway, are more trivially agreed on, like a proof involving lemma. If I change the order of the lemma, often maybe if it's possible, they're going to be considered two different presentations of the same proofs, or like minor changes of notation of proof written in different fonts. Certainly, that's going to be a property of the presentation and not the proof. Even the language, like the same proof can be presented in English or Italian, for instance, or French. So, but we have evidence for the fact that there is no context-independent identity condition for proofs. It's going to depend on the matter. And in this context, I'm going to be concerned on a concept of proof that tracks epistemological properties that matters in practice. So another suggestion that I think resonates well with practicing mathematician is by McLean. And the idea is like a proof is not just a series of individual steps, he says, but a group of steps brought together according to a definite plan or purpose. So we affirm that every mathematical proof has a leading idea, which determines all the individual steps and can be given a plan of the proof. So the idea is like, okay, if the same idea is the same main idea, is invariant, then it's the same proof. But wait a second, epistemological differences may be relevant to the way we want to identify proofs. And here, I really like this passage by Marcus Giaquinta that tries to make this point clearer. So he says, usually mathematicians are happy to regard two presentations as presenting the same proof if the central idea is the same in both cases, or maybe if it's easy to go from one to the other. But if one main concern is with what is involved in thinking through a proof, its central idea is not enough to individuate it. Because if we do epistemology, we are also concerned with actual belief of actual people and on what these beliefs are based on. And this is gonna be affected by the way we think through these arguments. So Giaquinta continues, the overall structure, the sequences of steps, and perhaps other factors affecting the cognitive processes involved will be relevant. But then he comments, and his is also very important, even so, not every cognitive difference in processing following a proof will entail distinctness of proof. In some cases, presumably, the same bits of information in the same order can be given in ink and in Braille. And this is precisely goes along the line, so the distinction I gave you before between enabling and constitutive properties of a mathematical notational system. If I change the enabling property, that's going to be a merely cognitive difference, perhaps very important, but it's not going to be tracking epistemological differences. So if we individuate proofs in a way that is sensitive to the particular reasoning needed to grasp how they support their conclusion, then going from a topological proofs involving visualizations like the one I showed you with cutting and paste or the knot diagram case to a diagram-free proof would be a significant change, since the type of reasoning, the type of visual imagination would be completely lost. This doesn't mean that the proof cannot be converted at all, but that the proof that we would associate would not preserve the topological reasoning. Even for proofs involving knot diagrams, as I mentioned, it's easy to see how they could be converted in a purely symbolic proof. Even like the simple proof that complicated knot diagrams was in fact simplifiable into the unknot. I can just replace everything with sequences of numbers, fine. But I'm sure you would not have the same reason for that belief if I gave you the code proof. And it's even easier, of course, for algebraic diagrams. So what are plausible criteria of identity for proofs in this context? So in the present context of investigation, the philosophy of mathematical practice, the main concern is with the epistemic benefits and drawbacks for someone working through a proof. So we are concerned about justified beliefs based on our grasping of particular arguments. So understanding the arguments in the sense of having a grasp of what motivates major lines of arguments so that the large-scale structure comes into view is a major epistemic benefit. For example, it works against efficiency if, in order to see why certain steps are valid, one has to hold in mind a heavy load of formulas, like in the case we want to do the diagram chasing without a diagram, which later step may depend, or search back frequently to find the immediate premises on which the steps depend. So like we would have a lot of working memory problems. In fact, what we would do, if we have a proof like that without the diagram, what people actually do, they just write the diagram. So they make it themselves. So in this context, if one proof presentation is significantly better than another with regard to epistemic pros and cons, then they present distinct proofs. So back to arrow diagrams, I gave you that little step from Massey. Here it is again, and here again, like it's very easy to code this and to just eliminate the diagrams. I chose the convention Z for the zigzag, and I can just like write it down without the diagrams. But again, like what would you understand, what would you base the belief on the classification theorem on would be a different argument, I think. So in order to go through the algebraic proof, a mathematician would generally recreate the arrow diagram. So again, this either you recreate the arrow diagram and then we are back to the starting point, or perhaps we could do something else, something more radical. Why don't we spell out rules of manipulations of the codes themselves? Like rules that correspond to the diagrams, we can do that, fine. After listing such rules, we could check the correctness of the diagram-free proof without having to invoke the diagrams whatsoever. So it would be different. But even in this case, the diagram-free proof presentation, I think it's plausible to say, does not present the same proof as the diagrammatic proof presentation. This is because the two presentations differ with regard to epistemic benefits and drawbacks, and even to the subject matter of what they are about. But this doesn't mean that it's not easy to translate one or convert one into the other. In fact, it's very simple to do that. And I think this type of consideration suggests that thinking that if you can convert easily one proof into another, then they are the same, this is not a valid principle in the context of the epistemology of mathematics. It might be useful for certain other analyses. So the diagrammatic proof presentation requires the reader to visualize specific spatial manipulations and recognize their validity. The diagram-free proof does no such thing. So we have like code manipulations. It is not only much easier to go through the diagrammatic argument, but it also allows us to grasp the proof more vividly. Moreover, I think the subject matter even of the proof differs. One is about surfaces, which we represent intuitively with arrow diagrams, and the other is about algebraic words, which represent surfaces only indirectly. So here, then, I suggested that the diagrams are indeed essential for these topological proofs. What about commutative diagrams? If we convert the proof into a diagram-free counterpart, a mathematician would generally be able to reconstruct herself the diagram in order to go through it, as I said. Without the diagram, it is much, much harder to grasp the large-scale structure of the proof and what motivates also the various steps. Also, for small-scale grasping, diagrams play a key role. They allow the reader to have a place to return to in order to check whether the algebraic manipulations are correct. So we go back and forth constantly between text and diagrams. And also, it seems fair to say that we need a diagram to perform the diagram chasing technique. We identify proofs by saying, oh, these are proof by diagram chase. So it seems like if I take out the proof, this is not anymore a proof by diagram chase, and this suggests it's not only a different presentation, it's a different proof. So let me just finish with some concluding remarks. So first, diagrams, I suggested, can form notational systems in mathematics. The perceptual features of notational system, and in particular of diagrammatic notational system, are divided into enabling and constitutive, and the later satisfy three requirements of clarity, reproducibility, and usability. And this is explains why diagrams can be used in proofs, in rigorous proofs. And we can go on and say that some diagrams exploit intuition or visual imagination in a regimented way, and this is the case of diagrams for surfaces or not diagrams in topology, but others do not. They are akin to algebraic notations in 2 dimensions. And from the perspective of mathematical practice, a significant difference in the overall epistemic advantages of the presented proof entails that the proofs themselves are different. These holds, even if they have the same informational content, these hold even if it's easy to convert one into the other. Therefore, from the perspective of mathematical practice, or better, from the perspective of an epistemology of mathematical practice, diagrams in the proof of the classification theorem for surfaces and the 5 lemma are essential to those proofs. So in a slogan, diagrams can be converted, but they get lost in translations. So, merci pour votre attention.